Okay. Hi guys. Sorry, it became a little late. Okay, so we'll continue. Hope everybody's there. Ah, okay. So yeah. So we'll continue. Right. I hope you remember what we were all seeing. Right. So I think we were seeing about yesterday we saw about reversible and irreversible work done. Right. And we went on to see what is this first law? Well, first law we already saw. So it was predominantly based, like the last class fully almost went on what is a reversible process and irreversible process. Someone tell me the points regarding reversible and irreversible? Like everybody can say one point, whatever they know. Please go for it.
Processes are very slow. Irreversible processes take place spontaneously.
Okay, fine. Hmm. Others? Quickly. What other things we saw? Okay, reversible processes are infinitely slow. Irreversible processes are spontaneous. Okay, so how will you understand that the question is coming from? I mean, the question is for irreversible process. How will you understand that?
It always has a constant external pressure.
Yeah, correct. So the process happens always under constant external pressure. So if you see the statement, that means that the process is going to be irreversible. Okay. So now tell me, how will the formula change for work done in an irreversible process and a work done in an irreversible process? How will the formula change with respect to W?
P external into V2 minus V1.
For
Work done.
Irreversible.
irreversible. Okay. For reversible.
For reversible, it's a integral dw equal to
Yeah.
integral
Correct.
v.
So you can write always the equation like W is equal to minus P dV from V1 to V2. So this is how you write the formula for W in a reversible process. See, this is reversible process. You have to always be integrated. Right. So what else we saw? Right. So I think that's the thing we saw, and then I explained you how can you visualize reversible and irreversible process, right? And obviously in the form of a graph, right? So how will you find the work done if I give you P versus V graph? If I give
By
you P,
finding the area under it.
correct, right? So you have to find the area under the curve, and obviously for a now, if you talk about expansion, people, right? If I talk about expansion, reversible expansion always gives me more work when compared to irreversible work done. So we'll just see that alone once, right? Because like we saw two different graphs for your reversible and irreversible, but I'll try to put it in the same graph. Then you'll be able to visualize how is it that the reversible work done is more than the irreversible work done, right? So we'll try to see that. And yeah, this was the last thing we saw, if you can remember, right? So whenever you have the first law, you're going to use first law. Delta E is equal to Q plus W, right? So delta E Q, no problem. They will be in form of joules always, right? But when you go to W, you have pressure and what is that? Volume, right? So generally it will be liter atmosphere. That's how in the questions, that's how they'll give you. So obviously you cannot directly add W to the equation, right? What do you have to do? You have to convert liter atmosphere into joules. And how will you do it? Liter atmosphere into 101.3. Give me the answer in joules. You have to remember this, people. If not, the entire problem is wrong. Okay, fine. So let me put the graph and then we'll continue. Okay, so like, I'm going to use this marker. Yeah. So if I plot a graph versus P external, obviously, versus V, right? Okay, so people, first let me draw for a let me draw for a reversible process. I know how the graph will look, right? So I know it's going to be a curve, right? Say I have some initial. Now, what is the thing? Like you'll obviously see that the external pressure, right, is going to keep on changing throughout the process because you saw like first 0.1 kgs, the external pressure will change. Second one again it will change. 90th one again it will change. 100th one again it will change, right? So obviously there are going to be so many partial pressures that are going to be included, and obviously say I start with some initial volume, end with some final volume here. So if it is expansion, obviously the graph has to go like this. Say the graph would have started something like this, right? Okay, cool, fine. So this is for an irreversible process. Now the question is, in this graph, right, where will the irreversible plot come? Is the next question, right? Now, people, right? So, like, let us go back to our examples. Like, I had one 10 kg mass, right? So the moment I removed the one 10 kg mass, what it go hit the stopper, correct? And it went on to T2V2 state, right? Okay. So, what is the external pressure? Now, in this, like, and in the sense, for the irreversible process, is the external pressure due to 10 kg mass, or is the external pressure due to atmospheric pressure? You tell me. Or have you understood my question? Right. So you put P external del V in your irreversible process equation W, right? So in the examples which we took, I saw one irreversible. The moment I removed the 10 kg mass, it moved up, right? Now the question is, what pressure value which I have to substitute? Whether it is going to be because of 10 kg mass, or is it after removing 10 kg mass, whatever the pressure is there, and obviously it is going to be atmospheric pressure. What do you think?
So you're asking which value to substitute in the equation.
Correct. So is it the external pressure is due to 10 kg mass, or the external pressure is due to, say, the after removing that I'll have some pressure obviously acting on the piston? Is it that pressure? Basically, it's the atmospheric pressure, right? So which pressure is going to be?
Is it after removing, sir?
Exactly, right. So please understand, people, right? It's all about now who's doing work. The gas is doing work. I told you, whenever expansion happens, gas is doing work. Whenever compression happens, the work is done on the gas. Correct. So in this case, expansion is happening, so the work is done by the gas, and work is done by the gas against what? Like what? The expansion starts when? The expansion starts only after removing the 10 kg mass. So obviously the pressure which is exerted, right, while the expansion is happening is the pressure of the atmosphere. That is after removing the 10 kg mass, whatever the pressure is applied on the piston, against that pressure only the expansion happens, right? So the easiest way to put it is the work is done against which pressure? The work is done against the atmospheric pressure, because when the 10 kg mass was there, it was an equilibrium, right? Right, when the piston was not moving. But the moment I remove it, due to the change in pressure, now the external pressure is atmospheric pressure. Because of that, it is undergoing expansion. So basically, the last P. So this is the atmospheric pressure. Obviously, you know that moment I remove the 10 kg mass, the pressure would have gotten reduced, right? Say this was the last pressure. That means after removing the 10 kg mass, this was the pressure. The mass, the point is my pressure, right? So obviously the graph, and I know, right, how the graph is going to look. The graph is going to be for an irreversible process. The graph is going to be what shape?
Rectangular.
Rectangular. The curve is
for irreversible, no, sir.
For irreversible, what is the shape of the graph? It's a rectangle because I took the area under the curve. What is the actual curve?
Straight line.
Linear.
Straight line? How?
Straight
Parallel.
line parallel to x-axis.
Correct. Right. So straight line parallel to x-axis. So now this is my constant external pressure. right? So obviously the graph will start here along with V1 and it will end like this. So the curved line is for reversible and this is for irreversible. And obviously, if you're going to take the area under the curve, for irreversible, the area is just this, right? And for reversible, the entire area under that curve is going to be the area under the curve. And obviously, the work done will be more for reversible expansion, right? Oh, no, okay. And more importantly, I told you whenever you go, you're going to draw a graph for thermodynamic processes. The arrow marks are very important. So the arrow mark goes like this, the arrow mark goes like this, expansion, right? Now, take a minute, right? And in your notebook, draw the graph for a compression process, right? Irreversible compression, reversible compression, and tell me which is going to have, in which case the work done is more. Go for it. Right? I'm talking about a compression process, right? So I'm asking you first, draw the graph. How do you think the graph would be for both irreversible and reversible? And tell me which will have, whether irreversible work done is more or whether reversible work done is more. Go for it and tell me the answer. So guys, today please bear with me. The class will go at least till 8:15, right? And I know you have 8:30 class, but still, like what happened is, I told you, right? Even I'm a student, right? So I'm doing my PhD. So even I have my exams today. I have my mid-semester exams, so I had to sleep little late in the night after studying. So that's how all this happened. So please bear with me for today. Right? Okay. I hope everybody would have drawn it. Right? Please don't sit idle. Again and again, I'm telling. Please do not sit idle. Okay, please. When I ask you to do something, I'm not asking you to do it for me. Right? I just want you to understand. Right. Anyways, so anybody wants to tell me? Okay, like there's no telling. Let me see. Okay, so this is for expansion. This is for compression. Okay, right. So you can just imagine the exact opposite of whatever happened. The example which we took, like say 10 kg, 1 kgs, 100, 0.1 kgs, like the same thing, except that instead of removing, you're adding, right? Initially, say assume that the piston was in equilibrium with the atmospheric pressure. Okay, so now what you do? You add 110 kg mass. What will happen? The piston will undergo compression, right? Now that is an irreversible compression. Now instead of adding 110 kg mass directly, I add 10 1 kg masses. First 1 kg, second 1 kg, third 1 kg, 10th 1 kg. So again, it is going to go to P2 V2, right? Again, it is compression. The V2 is lesser in this case than V1. Initial volume is higher, final volume is lesser. Okay, so like this you imagine, right? Say now, let me draw it for the reversible case. Okay, let me draw it for the reversible case. Say assume that I had the initial, okay, assume that the initial volume is here, V1, right? Say the final volume is this, V2. Cool, right? And obviously what you're going to see, in this case, the external pressure is going to keep on increasing step by step, right? So first 1 kg, little pressure, second 1 kg mass, more pressure, 10th 1 kg mass, very high pressure. So as you add the masses, the external pressure is going to keep on increasing, right? So in that case, say if I had started with say this one, say this is my P1, and obviously the pressure would have gotten increased. Say this was my last sort, P2, right? So I know how the graph will look. So you have to start with this point, initial pressure, initial volume, to the final pressure, to the final volume. Say this point is where you're going to end, and it is not going to be a straight line. it is going to be definitely a let me please bear with me. Okay, say that. Obviously this is my P1 and that is my P1. Okay, now the arrow mark is very important. The arrow mark now goes like this. Now in last case it is expansion, here it is compression. Volume has to decrease and pressure has to increase, right? Okay, now this is the graph. Okay, actually
For
I'll draw it.
reversible, no, sir?
This is for reversible. Yes, let me draw it one more time. Okay, fine. So this is how the graph is going to look, right? This is for reversible, obviously, right? Okay. Now, how the graph is again going to be exactly, the shape of the graph is not going to change, people, right? The shape of the graph is again going to be I'm talking about irreversible process, right? So the shape of the graph is not going to change. It is going to be a straight line parallel to x-axis, because again it is going to happen under constant external pressure. The compression is going to happen under constant external pressure. Now tell me, for this process, for this irreversible compression process, what is the external pressure? Like looking at the situation, we saw example, right? Now tell me, the external pressure is due to what? The constant external pressure you're speaking about, under which the compression is happening, right? Because of which I have the external pressure.
The mass which you put on it.
Correct, right? So it's because of the 10 kg mass. Correct. Now, last case, what happened? After you removed the 10 kg mass, the piston moved up. So in that case, the pressure is less, right? Because you removed the 10 kg mass. Now, in this case, already in equilibrium. Now you're adding 10 kg mass, and after that only the compression is happening. So basically, who does the work? The work is done by the 10 kg mass, right, on the gas. So definitely you have to now take a higher pressure. So obviously the P2, after adding the 10 kg mass, whatever the pressure I have, right, that would have been my external pressure, right? And obviously the graph would have gone like this. Is it not? Everybody accepts?
Yes, sir.
Any questions? Now this is for the irreversible one, right? Now tell me where the area is more, where the work done is more, for irreversible or reversible?
Irreversible.
Exactly, right? For irreversible, in this case, not only in this case, for any case of compression, whenever you have irreversible compression and reversible compression, work done during irreversible compression is greater. Whereas when I go for expansion, reversible expansion work is having more work. Will have the value, will have higher value of work. Is that understood? Anybody has any questions?
No, sir.
Okay, what about others? Everybody understood? Please give me a
Yes,
yes.
Yes, sir.
Understood.
Okay,
Yes, sir.
fine, cool. Right, so this is how the graph will be different for compression and expansion, reversible and irreversible. Cool, right. Now we'll move on. We will concentrate on the first law of thermodynamics, right? Okay, so we know how the first law mathematical form is delta E is equal to Q plus W. Is that okay? Right. So first, let me take, like I told you, right, this particular equation will be modified according to what kind of process I'm doing, right? I have different kinds of processes. Say isothermal, I told you isothermal processes where temperature is constant. I have isochoric process where volume is constant. Isobaric process where pressure is constant, right? And the last one would be adiabatic process, right? Adiabatic, I said no heat will be lost, no heat will be gained, so Q would have been 0, right? So we will see how this equation will change, right? How the equation will change for all these different processes. Is that understood? Right. So let me start with an isochoric process. Isochoric is constant volume process. The volume cannot change, right? Okay, That means it's a fixed vessel. There is no piston arrangement. It's just a fixed vessel or a closed arrangement where the volume cannot change. Right? Okay. Now what is going to happen? Right. Now let me put it the equation again. So I have delta E is equal to Q. Now instead I'll write W. And I'll write W in terms of P external del V. Right? If it's reversible or irreversible, doesn't matter, because I know that work term is not going to be there because there is not going to be any change in volume. So it doesn't matter how I write it. So minus P external del V is what I have. Now, since it is going to be isochoric, that is the volume cannot change. So definitely delta V is 0, is it not? V1 is equal to V2. So V1 minus V1 is equal to 0, right? So what I have in this? I have just delta E is equal to Q. Okay. Now people, right? Now I am going to connect. I'm going to go back to my heat capacities. Okay. So what do you see here? Here I have a constant volume process. Correct? Right? So can I call this Q as QV? What do you mean by QV is heat added or heat lost at constant volume. Again, Q can be negative or positive. I don't know. It depends on the process. Right? Okay. So what I'm telling is why I wrote QV here is because this is the Q or heat which is lost or gained at constant volume, because the process is isochoric. Right? Now, I know I have an equation like this for Q in terms of your CV and CPs, right? I know, for example, if it is 1 mole or, okay, if it is n mole of a gas, I know, okay, you tell me, what will be the equation? Tell me, Q is equal to, in terms of CP and CP, I mean CP and CV, what is the equation?
CP minus CV.
CP minus CV is R, that is Mayer's relationship. So Q, I know I like, okay, forget about CP and CV. Now tell me, for molar heat capacity, right? If I use molar heat capacity, how will the equation look? I know I have two types of molar heat, two types of heat capacities, right? Depending on what amount I take. I know Q is an extensive property, right? So it depends on the amount. So I have molar heat capacity and mass heat capacity, right? But it doesn't matter. Anyways, so what is the equation? Nobody remembers.
That MC del T, sir.
Yeah, that's the one. That's the thing. So instead of N, it's not M. We are talking about molar heat capacity. It is going to be NC del T. So we write it as like this: NC into del T. Correct? Where C is the heat capacity, N is the number of moles, and delta T is the change in temperature. Right? Hope you remember this equation. So much time we spent on this. Okay. So anyways, so I know the CP is a combination of whether the process is going to happen at constant volume or whether the process is going to happen at constant pressure. So this C is the sum of CP and CV, right? So this heat capacity is equal to CP plus CV. So I can rewrite this particular equation as NCV del T plus NCP del T. Please remember this equation for Q and delta T. This is how you connect. How do you connect my heat and temperature? This is the equation in which you connect, right? So now obviously the CP and CV are molar heat capacities. If I use M instead of N here, now at that time it is going to become mass heat capacity. But anyways, you will not be using mass heat capacities in chemistry mostly. Only in physics maybe you will be using. But here we know we are comfortable with number of moles, right? So Q is equal to NCV del T plus NCP del T. Correct? Okay. Now if I do the process at constant volume, like what I'm doing here in isochoric process. Okay, if I'm going to do the process at constant volume, how do you think this equation will change?
At constant volume, sir.
Constant volume.
Then only NCP del T will remain.
Only NCP del T will be there. It's opposite, right? Only NC CV del T will be there. What is heat? What is CV and CP? CV is the heat capacity if the process CV is heat capacity at constant volume. CP is the heat capacity at constant pressure. Please remember this, right? So when depending on what process you're going to do, if you're going to do an isochoric process where the volume is constant, you have to use only CV, right? If you see that the pressure is constant, obviously I have to use CP. Now in this case, it is going to be a constant volume process. So this term has no significance. CP is not going to be there because I don't have constant pressure. The pressure is changing, right? So now how will I write the QV again? So QV will be equal to NCV del T. So this is what do you mean by again QV? QV is the heat loss or heat gained at constant pressure. Sorry, at constant volume. So I have only NCV del T. Right. Again, what you have here from the first law, I got QV as equal to delta E, change in internal energy, and the heat lost or heat gained is equal. Right. So I'll be able to connect these two equations, and I will be able to get a beautiful equation for delta E. Right. So what do you think delta E is going to be equal to? So since both are QVs, I have delta E is equal to NCV del T. Is a very, very, very important equation, right? So delta E is equal to NCV del T. You have to know this. Okay. So how it comes again? Now there is one more way of defining delta E now, right? Now how will I define delta E? That is change in internal energy. Change in internal energy is equal to heat lost or gained at constant volume. As simple as that. Okay, heat gained or heat lost at constant volume is what is my change in internal energy. Okay, now you can ask me, sir, so only when I have an isochoric process should I use this equation? No, for any process delta E is same. Delta E is the heat lost or heat gained at constant volume. That's how I define it, right? So for any kind of process you can use delta E is equal to NCV del T for any kind of process. Okay, so the overall outcome for an isochoric process is delta E is equal to QV, right? And we got an equation for delta E from this. We derived an equation. This is the permanent equation for delta E, right? It is equal to NCV del. Okay, right? Cool. So that's one thing. Now we'll move on. So that's about an isochoric process. So you have to know this equation again and again. I'm telling you because it's very important for problem solving, right? Okay. So now let me take an isothermal process. That is obviously where temperature is constant, isn't it? Right. So again, I write my first law. First law again is delta E is equal to Q plus W. Right. Now, just now, I derived an equation for delta E. Right. What is the equation? I know delta E is equal to NCV del T. So I can substitute it here. Right. And Q and W, like say, okay, we can even write minus P external del V, or you can just keep it as W. Nothing changes. Okay. Right. Now what is happening in this process? In this process, I see that it is going to be an isothermal process where temperature is constant. This is constant temperature, right? So what do you think will happen? Delta T, which I'm having here, delta T is going to become 0. So definitely the whole thing becomes 0. So what I have is Q is equal to minus W. This is the equation for what is that? Isothermal process. The first law modifies like this. Okay. So what happened here? Isothermal process. In the last case I derived an equation for delta E. So delta E is NCV del T. So if it is a constant temperature process, delta T is 0, right? And obviously the equation will become Q is equal to minus W. Is that okay? Right. Cool. Next, we will go for an adiabatic process. We'll see what happens. Right. Fine. I can write it here itself. Okay, I have an adiabatic process, right? So adiabatic process, I know what is going to happen. I have Q is equal to 0. There is no heat loss, there is no heat gain. That's what you need to understand. So if I look at this equation, if Q is 0, I can directly write delta E is equal to W. That's it, right? So adiabatic process, no heat loss or no heat gain. So the equation will become delta E is equal to W. That's it. Okay, so now you can ask me, sir, what about isobaric? Wait for it, right? Isobaric I will introduce when I go for enthalpies. Okay, so at that time I will go for isobaric process, and you don't have to worry. Isobaric is constant pressure. There'll not be any much change to the equation. All the things stays because you don't have any delta P here, isn't it? Right. So delta E is equal to Q plus W will stay as such for an isobaric process, right? But in that case, Q will be QP. Actually, I can give you that. Like that, it's not a big deal. I can
So I
introduce it
have
now.
a doubt.
Yeah.
What was the name of the process where volume is constant, sir?
Isochoric process.
Isochoric, sir.
Yeah.
Okay.
ISOCHORIC. Isochoric. Okay, so let me go for that also. I go for an isobaric process where I'm having constant pressure, right? Okay, so I know the equation is delta E is equal to Q plus W, right? So let me rewrite the equation little like this. I write Q as QP. What is QP? QP is heat lost or heat gained at constant pressure, right? Okay. So again, I have the equation for Q. I have NCV del T plus NCP del T, right? Now in this case, since the process is happening at constant pressure, CV has no role to play. So this has no role to play. So I can write QP is equal to NCP del T, right? Now I'm going to introduce to you a new thermodynamic term, right? So the new thermodynamic term is what is called as enthalpy. Okay, enthalpy, right? Okay, now how do I define it? This is how I define it. Enthalpy, right, is the heat. Obviously, it is going to be a form of heat, right? So this enthalpy, right, is the heat lost or heat gained at constant pressure. Very, very simple, right? How do I define it? I define it as it is the heat lost or heat gained at constant pressure. And my enthalpy is denoted by the letter delta H. But again, I cannot find the absolute enthalpy. I can find only the change in enthalpy. Okay, so this QP, which I'm speaking about, which is equal to NCP del T. So this QP is nothing but delta H. I think I have to write it in QP will be equal to delta H, where delta H is the enthalpy. And what is the formula? Now, if we can connect QP is equal to delta H and QP, in this case, I found it as what is this? QP is delta H and QP is equal to NCP del T. So definitely I have another equation. Now I have another beautiful equation for your delta H. Delta H will be equal to NCP del T. Very, very easy. Right? So your change in internal energy, delta E was NCV del T, heat add or heat lost constant volume. For delta H, it is exactly opposite. It is the heat order or heat loss at constant pressure, right? So the equation becomes NCP del T. Okay, so I can rewrite this equation if you want for an isobaric process. If I rewrite this, if I rewrite the equation, I will just have delta E is equal to, now what is QP? QP is basically delta H plus W. This is what you will get for an isobaric process. Very simple, right? So how delta H came, it's all about how I defined it. Delta H is the heat loss, the heat gain, and constant pressure. So we're doing the process of constant pressure. So I wrote it as QP. So in that place, I put my delta H. That's it. Okay, so you will have a second part of this chapter entirely about this delta H only. Okay, the second part, thermochemistry, I call it, right? This is thermodynamics, so much of physics involved, right? But the second part is pure chemistry for different types of reactions, right? You will have different enthalpy values. We'll look into it, right? For now, you don't have to worry, right? So we saw all four different kinds of processes, right? Isothermal, isochoric, isobaric, and adiabatic. And you saw how the equation changes, and you have to remember two new equations, one for delta E and another for delta H. Delta E is NCV delta E, delta H is NCP delta E. Very simple. Okay, cool. Now we'll concentrate on two processes in a very depth manner, right? One is my isothermal, right? So isothermal, I can have reversible as well as irreversible. Again, adiabatic, I can have reversible as well as irreversible, right? So we'll concentrate on these two, right? Because that is there in the syllabus, and obviously the other two processes I have nothing much to do, right? So you don't have to worry about it. Fine. So let me go for it. Okay, so I'm going to take a reversible isothermal expansion of an ideal gas. Right? That was the topic, right? Reversible process, isothermal, constant temperature, expansion, work is done by the gas, right? And what kind of gas it is, I'm going to take an ideal gas, which is not in reality, obviously, because I'm going to make a derivation which is going to be based on your ideal gas. PV is equal to nRT equation I'm going to use. Cool. So we will move on. So I know how the normal isothermal process, I say I have delta E is equal to Q plus W. I know delta E is NCV del T. So del T will become 0. So the overall equation would be Q is equal to minus W. And there's nothing change, no change here, right? So it's all about how the work done is going to get calculated. That's it. So now how will I find the heat lost or heat gained in this process? Right? How will I find that? If I can find the W, if I can get an equation for W, right? The negative of the W will become equal to Q. Very, very simple. So all I have to do is derive an equation for W for an isothermal reversible expansion of an ideal gas. We'll try to do that, right? So let me go for W. Like we remember this equation, we'll come back to this and substitute if you want, right? So I know W, since it's an irreversible process, I can write it as minus P dV. I'll write it properly. Minus P dV from V1 to V2, since it's an reversible process. Correct, right? Now this pressure what I have, right? This pressure what I have, I am going to use my ideal gas equation and I'm going to write it in terms of V. So I know PV is equal to nRT, so I can write P as nRT by V. Oh wait, 1 second, people. Sorry, the P has to be inside the integration because pressure might also change because it's an reversible process. So I will write it as minus P dV. P is inside the integration. Only if it is constant, I'll be able to take it out. Right? Only if the particular thing is a constant value, then only I'll be able to take it outside the integration. Right? So here it's not constant. Right? So it is from V1 to V2. Okay. So now again I'm going to use this equation. P is equal to N into R into T divided by V using the ideal gas equation. No problem. So now what will happen? W will become minus nRT by V dV, obviously from V1 to V2. Right? Okay. Now if you look at this, number of moles will not change. R is the universal gas constant, and it's an isothermal process. So definitely T is also constant. Whatever temperature is there, that temperature is going to stay throughout the process. Right? So nRT, all these things can be taken out. Okay, and because all these are constants, only volume will change definitely. Right? So now I can rewrite this equation as W is equal to minus nRT dV by V from V1 to V2. Okay. Now is the integration part. Now this you might not know. Let me check whether you know or not. So people, like we'll come back to this. Integration of 1 by x dx is what? I know it's a thing, but you will study about it. Don't worry, right? So do anybody knows this formula? Basically, dx by x is what I have. Anybody knows? Fine. So then I'll gonna give you the answer. Right. Fine. So whenever you have 1 by x dx or dx by x, right? So it is turning out to be, it is equal to log of x, log to the base e, not log to the base 10, right? So whenever you have 1 by x dx integration, that will be equal to log to the base e x. Okay. I hope you have spoken about logarithms. Have we ever spoke about logarithms?
Yes, sir. Basics of log.
Yeah, so I thought exactly. It's all the basics of log, isn't it? So that is what we have here. Okay. So 1 by x dx. Always remember there are so many other formulas. I don't want to get into it. You will be anyway eventually studying them in your 12th class, right? So do not worry, right? So this one is little easy. These are just one-step answers. That's it. So 1 by x dx is going to be equal to log of x. But again, this is very important. This is not 10. This is e. So I can write my, sometimes instead of representing it like this, they will represent like this also. So whenever I put ln, right? Ln corresponds to ln corresponds to the base e, right? And generally, if I put only log, it represents log to the base 10. But anyways, right, you don't have to worry much about it. So it's basically going to be log or ln. And if you put log, you have to put base e. Ln, you don't have to put anything. Same thing, right? Now that is what I have here also. dv by v is what I have, right? Now instead of x, I have v. That's it, right? So what will happen to my equation now? W is equal to minus nRT. Now integral is gone. I have done the integration, so it would have become log v, log to the base e, obviously, log to the base e v. No problem. Now what is remaining is about my limits. These are what the limits. So it is going from v1 initial volume to some final volume. So that is also there. v1, v2. Okay. Now I hope you this at least you know. Whenever you have limits, what will you do, people?
We substitute it within v2 minus v1.
Correct. So basically, in this case, it is going to be log v2 minus log v1. What you have to understand is, after you get the equation, right? After you get the equation, you always go for upper limit minus lower limit. Upper limit is this, lower limit is this, right? So first you have to substitute the upper limit value minus, you have to substitute the lower limit value and subtract them both. Very, very simple, right? So I have W is equal to nRT. Now it will be what? Log V2 will be there. I substitute it minus log of V1 will be there. Upper limit minus lower limit. Okay. So again, I'm telling this is mathematics you will be studying. So we will not be using much of mathematics, but physics, yeah, you will suffer, right? So, but again, don't worry. I think your faculty, I think the math faculty and your physics faculty are same, so no problems. He will take care, right? So if at all next class ask him, sir, can you teach us the basics of integration? It is actually very helpful in physics also, and sometimes chemistry also, like this. It will be helpful. Okay, so please ask him. So I have minus nRT. Now what did I said? Upper limit minus lower limit. So basically I would have had log of V2 minus log of V1. This is what I have, right? Now I have my negative sign also. Okay, before that, fine, I have my negative sign. So I can actually put the negative sign inside. If I multiply the negative sign inside, it will become log of V1 minus V2, right? So I have nRT log of V1 minus log of V2. Isn't it? No problem. Okay. Now tell me, what is log A minus log B? I taught you the basics of logarithms. So when I have log A minus log B, how can I write it? I have log A plus log B, how can I write it?
Log A, B.
Correct, right? So please remember this, people. I have two operations on log which are very, very important. Log of AB. If I have multiplication inside the log, I can expand it like this. Log A plus log B I can write. When you have log of A by B, I will write log A minus log B. So multiplication becomes plus, division becomes subtraction. Remember this. Okay. So log A is equal to log. Yeah.
This is log with base E, sir. All
Any
this.
log for that matter. Base doesn't matter here. In this case, yeah, this is log to the base E. But in this case, the operation can work for any base. No problem.
Okay, sir.
Right? Okay. So that's we need to know. So I am wrapping this part. If you have taken it down, or again you can watch the video. So this is what I have. Now I have log V1 minus V2. I told you log A minus log B will be equal to log of A by B, right? So I have W will be equal to nRT log of V2 minus V1, and still it is to the base E. And generally we don't deal with log to the base E. We deal with log to the base 10. So how will you convert log to the base E to the log to the base 10? I think I told you. Did I tell you? So much mathematics involved. I know. Please don't get frustrated. Okay. Right? You remember how do you convert log to the base? I think I didn't tell you. Right? Anyways, now I'll tell you. Right. So please remember, whenever you have log to the base E to some A, right? And if you multiply this by 2. And if you have the log to the base 10 to A, if you want to convert it, right? What you do is that you multiply this equation by 2.303. Okay. So what you do, if you want to convert log to the base E to the log to the base 10, you just put log to the base E as log to the base 10, but you just include one more 2.303 in the multiplication. Okay. This you will be using at least 200 times in your entire course of 11th and 12th. Okay, this conversion of log to the base E to the log to the base 10, you will be using it so many times. So even if you don't remember this, you will eventually remember, because this is what you will be doing continuously. So do not worry, right? So log to the base E can be converted to log to the base 10 if I just multiply, include one more thing in the equation and put 2.303. Okay, so now this equation now is going to get me amazing results. So this W will be equal to, now I have to convert it to the log to the base 10. So I will include a 2.303 log, say nRT log, I wrote it as V1, it's not V2 minus V2 by V1, it is V1 by V2. Log of V1 minus log of V2, log of A by B, right? So it will become V1 by V2, and this is the equation which you have to remember for isothermal expansion of a gas. Work done in an isothermal reversible expansion of a gas is this 2.303 nRT log of V1 by V2.
So this is for any gas or only for an ideal gas?
Ideal gas. Obviously, we used ideal gas equation, right? It's only for an ideal gas. It will not work for real gas. I have derivations for real gases also, but it is not there for you, right? Again, A and B constants can be included on all this, and I can derive it. Not there for you. Maybe if you go to BSc levels, yes, you will study that. Okay, so this is the equation B equals. You have to remember the derivation. Derivation is important every time. Like so many times they would have asked you. Say they will ask you, and obviously you have to remember the end result also for the case of doing problems. Okay, so W, this is for an isothermal. This is only and only, see, the moment you see W, do not substitute this. This is only for a reversible isothermal expansion of a gas. Only if they tell you if it's reversible, more than even reversible, if they tell you it's isothermal, then only you can go to this equation, right? Lot of times I'm doing, just because you have your V1 and V2, right? People will go for, I have an adiabatic process, they'll substitute this equation. Nonsense, right? So you have to do this only for a reversible isothermal expansion of a gas. Obviously, compression, you just have to interchange the V1 and V2 and become V2 minus V1, V2 by V1. Anyways, that'll ask you or not, right? So this equation, you have to remember 2.303, N is the number of moles, R value. What is the R value, people? Here, in this case. R value is what? In this case. In this case, basically. What? Nobody remembers the R value? What are the different
8.314.
Yeah, right. So people, we are using, again, I told you, whenever you go to thermodynamics, mostly you will be using only joules, right? So whenever you have joules or whenever you have energy terms coming, that time R value should be 8.314. So please remember here, R value is 8.314 in terms of joules, and they will not ask you, but if they ask you in terms of calories, R value is 2. Okay,
So
if you
when
want
do
to
we know where we use calories and where to use joules?
It depends on the question. Generally, you will be using this. Say, for example, you go for JEE, right? And they ask you to find the work done. And it depends on the options. In the options, all the options are basically going to be calories. Then you have to use the R value as 2. And if at all it is all in terms of joules, then R value is 8.314. But in your school, I don't think you'll be using this. They're not going to ask you in terms of calories. It is only SI units. 8.314 is what you'll use. Okay, so for this, R value is 8.314, and temperature, do not forget, temperature should be in Kelvin, not degree Celsius. This we have already seen. Only SI units you have to substitute. If you substitute degree Celsius and do the answer, everything might be correct. Formula is correct, everything is correct. But due to a small mistake, the entire question is wrong. Right? So you have to know the derivation, you have to know the end equation, and you have to know what are all the constant values I'm going to use here. All these things are very important. Is that okay? Right? Fine, people. So I think we'll stop with this for today. I think next class, I think it will be on Monday, right? So please go through all this, whatever we have seen, right? We will do some problems. The entire class will dedicate to doing problems on this. Okay, because we are almost see, this chapter can be divided into 2 parts. One is thermodynamics, which you're seeing, right? The other is thermochemistry. As I told you, it's all about delta H, right? So I will be requiring, along with the problem solving session, some 3 to 4 classes for finishing thermodynamics itself, right? And I require again some 4 to 5 classes for completing your thermochemistry, right? So we'll complete it, and after that we go for equilibrium, and that's it. Your physical chemistry chapters are over. No more problems, no more numericals, right? But you will find other types of problem, other types of difficulties if you go for organic. Okay. So, anyways, people, that's it for today. Any doubts? Any questions?
No, sir.
Okay. So if there are no questions, you can leave. You can take 15 minutes rest. I left you 5 minutes early. You can go for it. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.